Hello everyone, welcome to my channel. In this video, I'll be evaluating double integrals. I have two examples that I would like to work on. If you are new to this channel, please don't forget to subscribe. Now let's start. So our first set of integrals, a double integral from 0 up to 3 and then from 1 up to 2 of x squared y dx dy. Now let me point out right from the beginning that if you have a double integral like this, the inner integral corresponds to the first variable here. We have dx, that will be our variable x, and then the second integral, the one outside here, corresponds to the variable y. So therefore, we start by evaluating the inner integral, that is, we integrate with respect to x, treating y as a constant, and then we end up with integration of y with the limits, these outer limits 0 up to 3, as it is indicated here. All right, so let's start then. Page 1, let me capture the integrals exactly how they are. This is our first set, so from 0 up to 3, and then from 1 up to 2 of x squared y dx dy. Now, like I said, I will start with integrating x, treating y as a constant. So this is going to be equal to 0 up to 3. If you allow me to use brackets there, I'm going to say from 1 up to 2 of x squared y, and then I have dx, close bracket. We must have dy outside like this. Right. Now, remember, when we integrate with respect to x, y must be treated as a constant. So I'm going to integrate x squared. Remember, we add 1 to the power and then divide the result. So this is going to be the integral from 0 up to 3. The inner part is, remember, x squared. We add 1 to be x power 3, and we divide that by the same result. And then we have y there, which is a constant. Limits of integration. Let me use these brackets here. I'm going to keep these ones. Limit of integration from, remember now we have two variables. We have to state that we are actually evaluating from x equals 1 all the way up to x equals 2. Right, like this. And then we have dy outside. Now y is a constant and 3 is a constant. So this is y over 3. We take it out and then we substitute 2 into that place and 1 into that place. So this is going to be the integral from 0 up to 3. What are we saying? We are saying we have y over 3, and then we have, watch this, we have 2 cubed minus 1 cubed. What have I done? I've taken 2, substituted into the place of x there, and also 1. But we have to subtract because upper limit minus lower limit, that's how we evaluate integrals. And then we're saying outside there we have dy. Now let's simplify what we have inside. This is 8 minus 1, that's 7. So it will be 7 over 3y. So this is equal to the integral from 0 up to 3 of 7 over 3 y. And what are we having now? We're having dy. Now 7 over 3 is a constant. We can take it out of the integral, 7 over 3. And we're integrating from 0 up to 3 of y dy. Now what do we say? The integral of y, remember there is a power of 1 here on y. We add 1 and then divide by the same result that we get. So let's go to page number 2 here. And yeah, so basically I'm saying this is equal to 7 over 3 outside there, remember, and then we have y squared all over 2. And limits of integration, if you allow me to use brackets here, limits of integration, now we have only one variable. I just have to say 0 up to 3, like that. Now remember, 2 is a constant. I can also take 2 out. And then 2 and 3 will have to multiply to give me 6. So this will be 7 over 6. And what are we saying? Take 3, put it in that place where there's y. It will be 3 squared. And then put 0 there and subtract. This is 9 minus 0 is 9. So what we have is 7 over 6 times 9. Let me use that sign from application. And we say 3 into 6 is 2. 3 into 9 is 3. 3 times 7 is 21. And all over 2. This is our final solution. Right. What I want to do now is to change the order of integration. Remember, we said here, we started with integrating with respect to x because we have dx inside and then dy. Now I want to swap. I want to take this limit out. I mean, this integral out, this integral in, take this dx out and dy in. In other words, these limits of integration correspond to y, these limits of integration correspond to x. So I want to start with integrating with respect to y, and then I'll end with respect to x, and let's see what we get. So now I'm going to start from here. I'm saying now we're still on page 2. I'm saying changing the order of integration. We get what I told you. What do we get? From this integral here, we're starting with integrating with respect to y. So we have to form now, we have to say now, integral from 1 up to 2, and then integral from 0 up to 3 of, we're still having x squared y, but now we have to say dy dx. Remember, look at how this one is. Changing order of integration, we take this integral out, this in, we take dy in, dx out, like this. Right, let's see what we get. Again, like I've done in the first part, like I've done here, I'm going to have to introduce brackets there just to show you that we start with, in this case, y, and then we end up with x. So this is going to be the integral from 1 up to 2, open brackets there, integral from 0 up to 3 of x squared y, and then we have dy, and we close brackets, dx outside, like that. Now we're integrating with respect to x and y, with therefore x squared must be treated as a constant. I'll take that again. We are integrating with respect to y, and therefore x squared must be treated as a constant. Let's go to page 3. We perform what I've just said. All right, so what we're saying now is that will be exactly equal to the integral from 1 up to 2. Inside there, we have to integrate. Remember, we're integrating with respect to y. So x is treated as a constant. So y has a power of 1, we add 1, and then we get 2. We're going to divide that same number into y squared. So what we're having now is, let me use brackets there. We're having x squared, which is a constant, and we're having y squared all over 2. Limits of integration, we are now saying, remember, we have two variables there, so we have to say y is equal to 0 all the way up to y equals 3. And what do we have outside? Dx. Now, remember, x squared over 2, that's a constant, but y is what we're interested in. So this is going to be the integral from 1 up to 2 of what? Of x squared over 2, and then we're saying put 3 there, it will be 3 squared. Put 0 there, it will be 0 squared, like that. Right, and then we have dx outside. Now this is 9 minus 0, that's 9, and so we have 9 over 2 x squared. So this will be the integral from 1 up to 2 of 9 over 2 x squared, and then what do we have? Dx. Take 9 over 2 out because it's a constant, 9 over 2, and then we have integral from 1 up to 2 of x squared dx. Remember, using power rule, we have to add 1 to 2 to form 3, and we have to divide by the result. So this is 9 over 2, and what are we saying? We're saying we have now x power 3 all over 3. Limits of integration from 1 up to 2. One variable now, I don't have to say x equals 1 and all the way up to x equals 2. Now, notice something. Again, 3 is a constant and it's dividing, so I must take it out. So it will be multiplying with these 2 here. So what do I have? Now I have 9 all over 6 because 3 times 2 is 6. And what do I have inside there? Put 2 there, it will be 2 cubed. Minus, put 1 there, it will be 1 cubed. Now what is 2 cubed? 8 minus 1, 7. So we have 9 over 6 times 7. Again, we see that 3 goes into 6 2 times, into 9 3 times. What is 3 times 7? Yet again, we're finding 21 over 2. So the order of integration doesn't really matter. So there's a theorem that we are going to talk about at the end. Very famous theorem telling us that the order of integration doesn't really matter. As long as you have two integral expressions, you have two variables, x and y. In this case, x squared y, and of course we are dealing with x and y as variables. these two functions are both integrable on these intervals 0 up to 3 and then 1 up to 2. Therefore, if that condition is satisfied, then the order of integration doesn't really matter. Right, let's look at our second integral in this video, given in a different format. We will have to convert it into the ordinary format that we're used to. Here we go. So we have to evaluate the integral. We have the function here, which is defined over or on a region R, and R is defined as a set of ordered values x, y, such that x ranges from 1 up to 2, y ranges from 0 up to 1. And we have dA there. Now remember, A comes from area. Area of a rectangle is length times width. And we're talking about x times y. So this can be replaced by dx dy. And so what we have there is we have x inside. So we'll have our limits of integration from 1 up to 2 dx, and then limits of integration from 0 up to 1 dy outside. Again, we start integrating with respect to x, and then we end up with respect to y. In this one, I'm just going to perform one integration. In other words, integrating with respect to x, then with respect to y, without actually changing the order of integration. I'll leave that one to you to try and check and see if you get the same result like we have seen in example 1. All right, so let's go through this then. Right, so we are basically saying that we have to change this format. So what we have, number 2, as it is given, integral, two integrals defined over a region R, and we're told that the functions are 3x plus 2x squared y squared, and we're told this is dA, and it is given that R is a function, is a region defined by ordered pairs x, y, x, y, such that x ranges from 2 all the way up to, or let's say from 1 up to 2, and y ranges from 0 up to 1, like so. Right, so now we're saying this basically is the same as the integral. Remember, the outer integral will have limits 0 up to 1. The inner integral will have limits 1 up to 2 of what? Of this expression, 3x plus 2x squared y squared. And then we're saying, remember what I told you, dx dy. Now this now is in this format here, this format. So now we perform the integration with respect to x, and then we end up with respect to y as follows. So we're now saying this is equal to the integral from 0 up to 1. Let me use brackets there. Integral from 1 up to 2 of 3x plus 2x squared y squared, 2x squared y squared, and we're saying we're integrating this with respect to x first, and then we will end up with the integration with respect to y, like that. Now we have to perform integration of these terms here with respect to x, and therefore y squared has to be treated as a constant. So let's start from here. Remember, 3 is a constant, but I'm interested in x, so this is the same as integral from 0 up to 1 of what? Here we're saying 3x squared over 2 plus, remember, 2y squared, we have to say x cubed over 3, right? Remember, we're integrating with respect to x first. Limits of integration, if I use brackets here, I'm going to say limits of integration. Now remember, we're talking about x now. X equals 1 all the way up to x equals 2. Why? Because we have two variables here, so we have to specify that we're interested in x first, and we have dy outside. Now notice that 3 over 2 is a constant, so we can simply take it out, and then we substitute 2 there, and same story here, we're going to substitute 2 in that place, and then 2y squared over 3 will be taken as a constant. We do the same for 1 and subtract. Right, so what are we saying? We're saying this is the same as integral from 0 up to 1 of what? Let me take this one like this, 3 over 2, and then I'm going to say, open bracket, 2 power 2. I'm fine with this 2 here. And then I'm coming this part here, I'm going to say plus 2y squared, and then I'm going to say in that space, let me say 2y squared over 3, and then I'm going to say there 2 power 3, and then I have minus, let me use another bracket there. I'm going to do the same but now with 1. So 3 over 2, and then I must have 1 there, and I have to square it because that to be squared, and then plus 2 over 3 y squared, and then I have to say 1, and I have to say cubed. Let me close the bracket there. I'm done with simple substitution. Let's now clean up, taking us to page 5. Right, here is our page 5. Right, there we go. Now let's do the cleaning up here now. This is equal to the integral from 0 up to 1. Inside here, if you check, that's 4 divided by 2, and that's 2 times 3, that will be 6. So I have 6 there, and then I have to say plus. This part here is 8. 8 times 2 is 16, so I'm going to have 16 over 3 y squared. 16 over 3 y squared, and then I have minus. I have to simplify that expression first. This is just 3 over 2, and that will be 1, of course, times that, it will be 2/3 y squared plus 2 over 3 y squared, like that, and then dy outside. Forgot to write dy here because we have to integrate with respect to y. Yeah, we have to integrate with respect to y there. There is your dy. We have to have dy here also. Let me just move this one down so you see what I'm pointing at. There's your dy. We need to have dy here, and we're also having dy there. Now let's simplify this part inside there. So this is going to be the integral from 0 up to 1 of what? Inside there we have 6 plus 16 over 3 y squared minus 3 over 2 minus 2, let me say y squared over 3. Right, and then I have dy outside. Now let's simplify this. This and that can simplify, and those two can simplify. Now this, I'm going to write it as 12 over 2, and then minus that. So now we're saying this is integral from 0 up to 1 of 12 over 2, that is 6, and then I'm saying minus 3 over 2, and then plus, this is 16 y squared over 3, and then minus 2 y squared over 3. And what do I have outside there? Y. This is 9 over, you can see 12 minus 3. Let me take it slowly. 0, integral from 0 up to 1 of 12 minus 3 over 2, and then plus 16y squared minus 2y squared all over 3, and then we're saying dy outside there. Now this is 9 over 2, so this is integral from 0 up to 1 of 9 over 2, and then we are saying plus, this is 14 y squared over 3 dy. Now let me distribute this integral and the dy. This is now single variable where we have there now, and this is a constant, so maybe step by step, 0 up to 1 of 9 over 2 dy plus, here I'm gonna say integral from 0 up to 1 of 14 y squared over 3 dy. 9 over 2 is a constant, I can take it out, 9 over 2, and then I'm gonna say integral of 1 dy. What do we have from 0 up to 1, and then plus 14 over 3 is a constant, I'm taking it out. Then I'm going to say integral from 0 up to 1 of y squared dy. Now integral of 1 with respect to y is y, so this is 9 over 2 y. We're evaluating this from 0 up to 1, and then plus, I hope you can see there, let me move it up so you're able to see that part there, and then we're going to have here 14 over 3. Integral of this is y cubed over 3, and I'm going to do this limits 0 up to 1 like that. Now I can take the 3 out also if I want, just to simplify matters. That takes us to page 6. Right, you're able to see, yes. So this is 9 over 2. Put 1 there, you're going to have 1, and then put 0 there, because we have to put the upper limit and lower limit and then subtract. Plus this, take 3 out, that will be 14 over 9. 3 times 3 is 9, and then we're saying put 1 there, it will be 1 cubed, and then put 0 there, it will be 0 cubed. What are we having now? This is going to be 9 over 2 times 1 is 9 over 2 plus 14 over 9 times, remember 1 to the power 3 is 1 minus 0 is 1 times 14 over 9 is actually 14 over 9. Now let's find the lowest common denominator there. It's 18. 2 into 18, that's 9 times 9, 81, plus 9 into 18, 2 times 14, that's 28. Adding those numbers up, we're having 109 all over 18. That's our final solution. Now, what I want you to do is to change the order of integration on page 4. Remember here we started with integration with respect to x, and then we ended up with respect to y. I want you to take this inner integral out, this one outer integral in, and take dy in, dx out, and perform the integration there. You should find the same result. You should find the same result. So that takes us to a famous theorem then, which is actually called the Fubini theorem. So it's the Fubini theorem. What does it state? It says that if you have two functions f of x and g of x defined over some region R, okay, so f of x and g of y, let me say, we want to have two variables here. Multivariable calculus we're dealing with, two variables. So we have two functions, f of x and g of y, integrable over a region R or on a region R. In other words, you should be able to integrate these two functions over on that region there. Firstly, with respect to x, and then with respect to y. He says that this one here should be exactly the same as the integral. Two integrals, of course, evaluating y first. So we're saying keep this one the way it is, f of x, g of y, but now we have to have dy dx. In other words, integrate with respect to y first and then with respect to x. The outcome should be the same as if you start integrating with respect to x and then you end up with integration with respect to y. So this is the famous Fubini theorem. I don't know if I pronounced that correctly, but yeah, that's a famous theorem. Order of integration is not important as long as the two functions are integrable on that interval or on that on that region R, some region R. Remember, we're dealing with two variables here, multivariable calculus. So as long as you can integrate the two functions on that region R, it doesn't matter whether you start with x or you start with y. You should come up with the same solution as you've seen in example 1. And this example here, I'm saying please go and do it, or find time to try and check if that is okay with you. You should find the same result, 109 over 18. Okay, I'm going to stop here. Definitely will come again with many more videos on multivariable calculus. We're looking at double integrals and triple integrals, and then we are going to look at applications of these in terms of volume and other aspects of differential calculus. All right, I am going to stop here. If you're new to this channel, please don't forget to support us by subscribing, and we truly value your feedback. All right, see you next time.